We continue our understanding of subsequences, and we will talk about the concept of subsequential limits or limit points. Okay, so we begin with the definition of what it means for a number to be a subsequential limit of a sequence. Consider a sequence xn. A subsequential limit is any real number or plus infinity or minus infinity such that it is the limit of some subsequence of xn. Okay, so remember, xn by itself need not have a limit, but it may have a subsequential limit if there exists some subsequence of that sequence which has that particular limiting value. Okay, so once again, subsequential limits are essentially limits. A sequence may have multiple subsequential limits, right? A real number or plus infinity or minus infinity is a subsequential limit of a certain sequence if you can come up with a subsequence of that sequence which tends to that number or plus infinity or minus infinity. Okay, and subsequential limits are also often called limit points. Okay, so in certain books or in certain references, you might find them being referred to as limit points rather than subsequential limits, right? These are exactly the same thing. Yeah, one trivial note based on results that we have already shown, that if xn in fact does tend to x, then x is the only subsequential limit. Right? This is something that we have already shown. Right? If you have a sequence that converges, then every subsequence of that sequence in fact converges to the same limit. Right? So if you have a convergent sequence, then the only subsequential limit of that convergent sequence will be the limit itself. Okay, so this is again a consequence of what we have studied. But we will now give a few examples of sequences that produce more interesting subsequential limits. Right? So let's say example 1. This is xn is equal to n times minus 1 raised to n. Okay, so stare at this for a second, pause the video if you need to, and think about what are the subsequential limits of this sequence. For all the even entries, so where n is even, this sequence is basically growing monotonically and linearly off to plus infinity. For all odd valued n, the sequence is basically decreasing monotonically and linearly off to minus infinity. So some thought should convince yourself that the set S, this is the set of subsequential limits. Right? Or the set of limit points in this case is essentially going to be infinity and minus infinity. Okay, it's easy to see that I can easily come up with a subsequence of the sequence which tends to plus infinity. Well, that's just a subsequence composed of all the even entries of the original sequence. Similarly, I can come up with a subsequence that tends to minus infinity. All you have to do is write the odd entries of the original sequence. And well, what you have to convince yourself of is that other than plus infinity and minus infinity, there is no other subsequential limit. Okay, so yeah, I'm going to leave that as something for you to think about. Why are there no other subsequential limits? All right, so yeah, this is something that you can think about. Let's now move on to yet another example. This example is actually something that I've alluded to before, that let xn be a listing of the rationals. After all, because the rationals are countable, it is possible to arrange the rationals into a sequence, right? Let xn be one such sequence, and let's ask, well, what is the set of subsequential limits of this sequence? Right? Again, you might want to pause, have a chance to actually think about this. In this particular case, the set of subsequential limits is in fact the entire real line union plus infinity minus infinity. All of these are subsequential limits of this sequence. Okay. Again, think about why this is true. This, if you really, is a consequence of the previous the theorem that we have proved in the previous video, right? Obviously, plus infinity and minus infinity are subsequential limits. Well, that is also something that you should be able to convince yourself of. But so is every real number. In other words, if you have any listing of the rationals, and you pick any favorite real number of yours, you can come up with a subsequence of the sequence of rationals which converges to that real number that you chose. Okay, so this is in fact a consequence of the theorem that we proved in the previous video. All right. So again, think this through. I'm going to give yet another example. In this case, example is that xn is equal to n times 1 plus minus 1 raised to n. Right? This is again an engineered funny sequence which behaves very differently on the even entries and the odd entries. All the even entries are basically, if you ride along the even entries, you increase monotonically, linearly to plus infinity. At the odd entries, you basically are 0. So again, with some thought, you should be able to show that the set of subsequential limits is basically 0 and plus infinity. These are the only possible limits you can obtain from subsequences of this sequence. Okay, so far what we have done is simply defined this notion of subsequential limits or limit points. Subsequential limits are all possible limits of subsequences of a given sequence. Okay, that's our definition. Now let's move on to proving some properties of subsequential limits. Okay, so our first and main result is the following. Let xn be any sequence. There exist monotone subsequence. There exists a monotone subsequence of xn whose limit is the lim sup. Remember, every sequence has a lim sup. So the first part of the theorem is that for any sequence, I can come up with a monotone subsequence of that sequence whose limit is in fact the lim sup. Similarly, you can come up with a monotone subsequence whose limit is the lim inf. Exists. All right, so that's the statement of the theorem. in the language of the definition of subsequential limits that we have just gone through, another way of saying this is that lim sup and lim inf are always subsequential limits. So for any sequence, lim sup of xn and lim inf of xn are subsequential limits. Right? So that's the moral of this result. Okay. So now let's go through the proof. So the proof is actually remarkably straightforward, and in fact it builds on again that important result that if you remember in the previous video we proved this result of the conditions required for there to exist a subsequence having a certain limit, right? All we are going to do is leverage that, right? Because subsequential limits are precisely the set of those possible limits of subsequences of a given sequence. Okay, so so what I'm going to do is restrict my proof to the lim sup, and lim inf proof is going to be similar, right? We only consider right, the lim inf part is analogous, and again that can be left as an exercise. Okay, so what I have to prove here is that for a given sequence I can come up with a monotone subsequence whose limit is the lim sup of the sequence. Okay, now let's first get the trivial cases out of the way. If the lim sup is plus infinity, right, this means that the sequence is unbounded, right? Unbounded from above. And in this case we have in fact already shown as part of the theorem in the previous video that I can construct a monotone subsequence which tends to plus infinity. So done. Right? So if the lim sup is plus infinity, well, we have already constructed a monotone sequence which tends to plus infinity. So done. Similarly, if the lim sup is minus infinity, well, that implies then lim inf is also minus infinity. Right? And in this case, we have already constructed monotone subsequences that tend to minus infinity. Okay, so these two cases in fact follow directly from the theorem that we have already done. Now let us consider the third case where the lim sup of the sequence is a real number, let's say x. Okay, now I need to show that there exists a monotone subsequence of the sequence that converges to x. Alright, now pick some epsilon greater than 0. Now we have already seen that the necessary and sufficient condition for there to be a subsequence of the sequence which converges to the limit x is that for any positive epsilon, there are infinitely many entries of the sequence which are within plus minus epsilon of x, right? So it suffices to show that this set has infinite cardinality n such that xn minus x is less than epsilon. This set is infinite, right? Then again, from the result that we proved in the previous video, it follows that one can construct a monotone subsequence of the sequence which converges to x, right? Now, how do I go about proving this? First, we used, of course, the definition of limb soup. Since there exists some n naught such that soup xk now remember this object, this is exactly what we have been calling Vn, specifically it's Vn naught, right? So because this Vn sequence converges to x by definition, there clearly exists some n naught such that the value of that sequence is less than x plus epsilon, right? In particular, this is true not just for n naught, but every n greater than n naught, right? But again, at this point, this is all I need. So the fact that the supremum of the tail is upper bounded by x plus epsilon implies every entry of the sequence beyond n naught is upper bounded by x plus epsilon, right? Because the supremum is upper bounded by x plus epsilon. And that automatically implies that the cardinality of the number of elements or cardinality of the set of elements of the sequence, which is less than x plus epsilon, is infinity. Why? Because this set includes every entry of the sequence to the right of n naught. Okay? So one side is easy. Now to show that this is all that remains to be shown, right? I have already shown that there are infinitely many elements of the sequence which are less than x plus epsilon. If I also show that there are infinitely many elements of the sequence which are greater than x minus epsilon, then I would be done, right? Right. To show this, assume the converse. Okay. What does assuming the converse mean? Well, assume that this set actually had finite cardinality. If it has finite cardinality, then beyond a certain point, let's say n1, there would be no entries that belong to this sequence. This implies that there exists an n1 such that xn is in fact less than or equal to x minus epsilon for all n greater than or equal to n1. But that is a contradiction, right? It's a contradiction because the limb soup is in fact x. So if the sequence were in fact less than equal to x minus epsilon beyond a certain point, that means that the limb soup is at most x minus epsilon. That's a contradiction. Right? And that completes the proof. Alright, so that essentially tells you that the limb soup and using an analogous argument, the lim inf of the sequence are both limit points or subsequential limits. And moreover, you can come up with a monotone subsequence of the sequence whose limit is in fact lim soup or lim inf. Okay, so that's the first connection that we have made. We have made a connection between subsequential limits and lim soup and lim inf. Alright. Now let's move on to a couple of more observations that further kind of firm up this connection between lim soup, lim inf and subsequential limits. Okay. So let S denote the set of subsequential limits. Alright, so let S denote the set of subsequential limits and the following three statements are true. Firstly, S is non-empty. Secondly, the supremum of S is in fact the lim soup of the sequence. The infimum of S is in fact the lim inf of the sequence, and finally the limit of the sequence exists is equivalent to saying that S has a single element, which is of course the limit, right? So some of these statements are actually already well understood. So this is mostly a summarization. Specifically, the first part is trivial, right? Because we know that every sequence has a lim sup and the lim inf and a lim inf. These may be two different numbers or they may be one number, but we have already shown that lim sup and lim inf are in fact subsequential limits. So it's obvious therefore that S has to be non-empty. Similarly, we already mentioned that the limit existing is equivalent to saying that every subsequence of the sequence has to tend to the same limit. In which case, obviously, the set of subsequential limits is going to be a singleton set containing only the limit of the sequence, right? So 1 and 3 are trivial. And perhaps what I could do is, kind of quickly give you a sketch of 2, although this also can be an exercise. So I invite you to basically think about this on your own before actually referring to the proof that I'm actually going to give. Alright, so what does it mean to say that the supremum of the set of subsequential limits is the lim sup? Right? Note that lim sup clearly belongs to S. Right? So when I say supremum of S is equal to lim sup, what I'm really also saying is that the lim sup is an upper bound on S. In other words, the lim sup is greater than or equal to any other subsequential limit of the sequence. Similarly, to say that the infimum of S is lim inf, and noting that lim inf of already belongs to that set, to say that its infimum is equal to lim inf is equivalent to saying that the lim inf is in fact a lower bound on S. In other words, every subsequential limit of the sequence is greater than or equal to the lim inf. Right? It turns out this is actually not at all difficult to prove. Consider any limit point or subsequential limit. Consider any limit t of a subsequence. Okay, so suppose there is some subsequential limit t. Clearly there is going to be some subsequence x and k whose limit is in fact t. Okay, in that case we know that t is equal to the lim inf of x and k, of course. In this case the lim inf is with respect to k, and is also equal to the lim sup of x and k. Right, this we have already studied. Now the thing to note is that since nk, right, which is the index corresponding in the original sequence corresponding to the kth entry of the subsequence, nk has to be greater than or equal to k, right? Because nk has to be an strictly increasing sequence of naturals, right? So nk has to be greater than or equal to k. We have the following. The set of values taken by the subsequence, okay, for positions to the right of n is in fact going to be a subset of the set of positions taken by the sequence to the right of n. Okay. Once you are convinced of this, it follows that the supremum of the former set is going to be less than or equal to the supremum of the latter set. Similarly, the infimum of the former set is going to be greater than or equal to the infimum of the latter set. So, a direct consequence of this is the following. So, if you look at the lim sup is going to be less than or equal to, well, the lim sup of this set. Maybe I should write this as yeah. The lim sup of xn is after all the limit of this set. The lim sup of x and k is the limit of this set, right? If since for every position capital N, the the value of this, the supremum of this is going to be less than or equal to the supremum of this, it follows that the lim sup of x and k is going to be less than or equal to the lim sup of xn. Now, but the lim sup is exactly the same as t and is also equal to the lim inf. Right? And an analogous argument would show that this is in fact greater than or equal to the lim inf of my sequence. Okay? And this itself shows that t is going to be less than or equal to the lim sup of the original sequence, and t is going to be greater than or equal to the lim inf, which implies that in fact, yes, and since t is any arbitrary subsequential limit, it follows that the lim sup is an upper bound, lim inf is a lower bound. Right? And that shows that in fact, so that basically gives us another nice interpretation of the lim sup of a sequence. Right? The lim sup is in fact the largest possible subsequential limit of the sequence. The lim inf is in fact the smallest possible subsequential limit of the sequence. Okay, so with that interpretation, we are almost done. What I'm going to do is state one final result, which is basically going to be an exercise for you. Right. So this result has something to do with the closure of the set of subsequential limits. Once I write the statement, I will interpret it for you. Let S denote the set of subsequential limits of xn. Suppose you can, now this is clearly a non-empty set S that we have already seen. Let Tn be a sequence in S intersection R such that Tn tends to T. Okay, so this is still part of the hypothesis of the theorem. So let S be the set of subsequential limits. Okay, now S may contain plus infinity. In particular, if the lim sup is plus infinity, then S will contain plus infinity. So I'm going to construct a sequence Tn whose elements are in fact in the intersection of S and R, because I want a sequence by definition is real valued. So essentially I'm taking a real valued sequence which is composed of subsequential limits of my original sequence X. Okay, and suppose I can do this in such a way that this sequence Tn in fact converges to T. Then the conclusion of the theorem is that T also belongs to S. Right? So what does this really mean? What this means is that you consider the set of subsequential limits or limit points of a sequence. Now, if I can construct a sequence, made up of elements in that set S, any limit of that sequence will also be contained in S. So, right? And this is something that we will make more sense of later, but this has something to do with the closure of S. In other words, that if I construct a sequence of elements within S, the limit of that sequence, if it exists, will also belong to S. That's kind of the moral of this story, right? This may look somewhat complicated, but actually it's not. The proof is actually fairly straightforward. So if need be, we can discuss this in the one-on-one tutorial sessions, but it's actually fairly straightforward. right? All you really have to do is patch together the results that we have seen before. All right. So the moral of the story in this video is we have defined subsequential limits, right? These are the limits of subsequences of a given sequence. We have seen that the lim sup is always a subsequential limit. The liminf is another subsequential limit, and moreover, the lim sup is the largest subsequential limit. The liminf is the smallest subsequential limit, right? And the set of subsequential limits is like a closed set, quote unquote. And what does it mean to say that it is a closed set? That if you come up with a sequence from within that set, any limit of that sequence will also lie in that set, which is what this last result I have put down actually says. So I'm going to leave this as an exercise to you, and starting from the next video we will move on to series.